Hi everybody, this is a review for your third exam. This is a longish review, so let's get cracking on things. You got this a couple of days ago. Let's go through it now. Okay, so we have the cube root of 64. What we're going to do is we're going to look for things that we can cube to get 64. As it turns out, that's 4. So that means the cube root of 64 is 4. You'll have a question similar to that. You'll have a question similar to this. We have the 8th root of x to the 8th, where the index and the exponent are the same. We just divide out and get x to the first. Now, since this is an odd power, this x to the first, and we started out with an even root, even index root, we have to put that x in absolute values. If this ended up being an x to the fourth, well, we wouldn't have to do that because it would be an even power. Anytime this ends up being an odd power and the index is positive and it's not positive but even, then we have to put it in absolute values. Let's look at another one, another simplification of radicals. We have the cube root of 135. I'm going to look for a perfect cube in 135 times something else. And I'm going to look for the largest one. Well, as it turns out, 27 times 5 is 135. Why did I choose 27? Because 3 to the third is 27. So it's a perfect cube. So I rewrite it as 27 times 5 under the cube root. Then I take the cube root of each separately. There should be a little 3 here that I forgot to put. And we have 3 cube root of 5. Simplifying a fraction underneath a square root or a cube root or any kind of radical, we have 2 choices. We could keep the entire fraction under the square root and try to reduce, which is what we did here. 252 divided by 7 is 36. And y to the 17th divided by y to the 7th is y to the 10th, subtracting the exponents. The square root of 36 is 6. And then we take y to the 10th. We take 10 divided by the index, which is 2. And that gives us y to the 5th. Since this is an odd power, we have to keep it in parentheses because the square root started out as an even power. Taking a look at 99x to the 17th. The 17th didn't turn out so well there, but it is 17. Anytime we have a variable underneath a radical and it doesn't divide out with the index, we rewrite. If it's even, we rewrite. We break the exponent up into 2 times 2 is the same basis, where 1 is to the first power and the other one is to whatever even power plus that first power gives us the exponent here. So in this case, it'd be 16 plus 1 gives us 17. So we break it up as x to the 16th under the square root and x to the first under the square root. So dividing out, we get x to the 8th, and then we still have the square root of x on the square root. And then the square root of 9 for 99 is 3. And I can't do anything with the square root of 11. So we get 3x to the 8th, square root of 11x. We don't need the absolute value for x to the 8th because this is an even power. Looking at a cube root example where we have a fraction. Again, in this case, we start out with, in number 6, we start out with the cube root over a cube root. We can write that as a single cube root with the fraction underneath it and try to reduce. In this case, it reduces pretty nicely. 243 divided by 9 is 27. That's nice because the cube root of 27 is 3. And as far as when this is an odd index, how do we break this up? Well, we take the exponent and break it up into similar bases. So in this case, it'd be x to some power times x to some power like we did with the even root, but it's going to be the biggest power that the index divides into times whatever's left over. So in this case, the biggest power in 5 is 3. So to write this as x cubed, I'd have to write the next base as x squared because it'd have to add up to 5. And so that gives us the cube root of 27 times the cube root of x to the third times x, the cube root of x squared. Can't do anything with the x squared, but I can do something with the cube root of x cubed, and that is 3 over 3, which gives us x to the first. Don't need absolute values here because we start out with an odd index. When we're dividing by two terms, and one of those terms or both those terms have a square root in them, we multiply top and bottom by the conjugate. Remember, the conjugate is the same two numbers, just opposite signs. So this started as a minus, it's going to become a plus in the conjugate. So we multiply this out. 3 times 3 gives us 9. 3 times the square root of y gives us 3 square root of y. Square root of y times 3 gives us a 3 square root of y again. And the square root of y times the square root of y give us a square root of y squared. Squares and square roots cancel off, giving us just y. 3 square root of y plus 3 square root of y gives us a 6 square root of y. And then we have the 9. No like terms in the top, so that's our numerator. In the denominator, we multiplied it also by the conjugate of the denominator. So we get 3 times 3 is 9. 3 times the square root of y is plus 3 square root of y. Minus square root of y times 3 is minus 3 square root of y. And minus square root of y times square root of y is minus square root of y squared. Squares and square roots cancel off, giving us minus y. Plus 3 square root of y minus 3 square root of y are like terms with like radicals. They subtract out to be 0, so we're left with the 9 minus y. That effectively gets rid of the denominator's square root. When we have a square root equation, we isolate the square root and then square both sides. And so the square root here is already isolated. When I square both sides, the square and square root here will cancel off, giving us minus x plus 12. And over here, this minus x quantity squared gives us a positive x squared. Going to set this equal to 0 by adding x to both sides and subtracting 12. That gives us x squared plus x minus 12. We can either factor or use the quadratic formula. I chose to factor. When I factor this, I get x minus 3 as one quantity and x plus 4 as the other quantity. So this means using the factoring method to solve this equation, x minus 3 equals 0, or x equals 3. And another possible solution would be x plus 4 equals 0, or x equals minus 4. So now let's check. When I plug minus 3 in, or 3 in rather, I get a minus 3 plus 12, which is 9. The square root of 9 is 3. And that would say 3 equals a negative x. Well, x was 3, so that means 3 equals negative 3. That's not true. So x equal 3 is not a solution. Let's try the minus 4. When I plug minus 4 in, we get minus a negative 4. Because remember, the x is minus 4, so this gives us a double negative, which becomes a positive 4 underneath the square root. And 4 plus 4 gives us 16. So the square root of 16 is 4. And then minus, because it started out as negative x, so minus a negative 4 gives us a positive 4. So 4 equals 4, so that's true. So x equal 4 is a solution. So we have one solution here, x equal negative 4. The other solution, x equal 3, can't be used. When we have a radical equal to a radical, whatever the index is, we power it with that index. So this is the index of 5. So we're going to fifth power both sides. Fifth powering both sides cancels out the fifth roots. And it gives us 3x minus 4 equals 2x plus 4. We're going to subtract 2x from both sides and add 4 to both sides, and this gives us x equals 8. You don't have to check to see if one or both solutions in an odd power index are valid. They will be, as long as it satisfies the equation when we check it. Okay, any solution will work here as long as we satisfy the equation. So in other words, if this was negative, it'd be okay. If it was positive, it'd be okay in some cases. Not in this case, but in some cases. When we have a negative underneath a square root, remember it pulls out as an I. So we're going to pull that negative out as I times square root of 28. 28 has a perfect square of 4 involved. So it'll be I times square root of 4 times 7, which is I times 2 square root of 7. Remember, we always put the I after the numbers. So we're going to put it at the end here as 2 square root of 7i. When we add complex numbers together or subtract complex numbers, we distribute and combine like terms. So I'm going to distribute this negative, giving me a positive 3 and a negative 4i. So I combine the 3 and the 7. That gives us 10. The 4, or rather 11i minus 4i gives us a 7i. When we multiply, in this case, we'll distribute. If this was 2 terms here, we do the foiling process. We have 3i times 3, which is going to be 9i squared, or I'm sorry, 9i. And we have 3i times minus 5i, which is minus 15i squared. Now keep in mind, whenever you see I squared, we'll replace it with negative 1. Okay? So it'd be 9i minus 15 minus 1, which is 9i plus 15. Now we'll rewrite into that a plus bi format as 15 plus 9i. The I part always goes second. We might have I to some higher power. If this is an odd power, we shed one I off. So in this case, it's 183. So that'd be I to the 182nd times I. That one was shed off. Now, this number will divide by 2. And so that's 91. So I'm going to write this as I squared times 91. Okay. I squared is negative 1. If this exponent is odd, then it stays as negative 1. If it's even, it becomes positive 1. Since it's odd, it's going to stay as negative 1. So negative 1 times I, or negative I, is our answer. We should be able to use the square root method. In this case, we have y squared over 4 minus 4 equals 0. I'll get rid of the 4 in the denominator by multiplying everything by 4. The common denominator here, like we did day 1 when we first looked at equations, I multiply by 4. That cancels the 4 out here, giving us y squared. Multiply the negative 4 by 4, giving us negative 16, and 0 by 4 is still going to be 0. I'm going to slide the 16 over to the side by adding it to both sides, isolating the square, and we get y squared equals 16. We'll plus and minus y squared, and we'll plus and minus the 16. Squares and square roots cancel each other off, giving us y, and then the square root of 16 is 4, so that gives us plus and minus 4. Remember, the plus and minus is 2 separate solutions. Should be able to use a quadratic formula. In this particular example, we have minus x squared minus 2x plus 8 equals 0. We prefer to have a as a positive 1. Since they have a negative in front of this x squared, it's negative 1. So to make it positive, we'll multiply everything in the equation by negative 1. So that gives us negative 1 times minus x squared, which should be x squared. Negative 1 times minus 2x will be plus 2x. And negative 1 times 8 will be minus 8. And then over on the other side of the equal sign, negative 1 times 0 is still 0. Now let's figure out what a, b, and c are from this equation that we multiplied by negative 1 with. So a is 1. That's great. That's what we want. We prefer to have a be positive. It doesn't have to be. It just prevents you from making some errors. B is 2, and c is negative 8. So x equals minus b plus and minus b squared minus 4ac over 2a in the quadratic formula. So every place I see an a, I put a 1 in parentheses. Every place I see a b, I put a 2 in parentheses. And then where I see that c, I put the minus 8 in parentheses. I work underneath the square root first and try to figure out what that is. So I put in my calculator with parentheses 2 squared minus 4, in parentheses 1, in parentheses minus 8. That gives us 36. So the square root of 36 is 6. So that's where that 6 comes from. So we have minus 2 plus and minus 6 over 2. Now let's simplify to get both answers. We have a plus and a minus. So let's look at the minus first. That's going to be minus 2 minus 6 over 2. Minus 2 minus 6 is minus 8. Divided by 2 gives us negative 4. Let's look at the positive case now. Minus 2 plus 6 over 2 gives us 4 over 2, or 2. So our solutions to that equation are -4 and 2. Let's graph the original equation before we multiply it out the -1. So we're going to start with the -x squared minus 2x plus 8. Since a is negative, it's less than 0, so the graph will open down. Since this is in standard form, we have to use the formula to find a vertex. X equals minus b over 2a. So plugging b in, we get -2. So we have a negative 2 over 2 times -1. So negative negative becomes positive 2 over -1, which is -2. I'm sorry, over 2, not -1. -2 over 2, which is -1. -1 quantity squared. Now I'm going to evaluate. -2 times -1 plus 8 gives us 9. So our vertex is at -1, 9. The y-intercept, when I let x equal 0, we get 8. Everything with an x drops out. The x-intercept was found in problem 15, -4 and 2. So now to graph. We make our x-axis with an appropriate scale, our y-axis with an appropriate scale. We plot the vertex, the intercepts of x, and the y-intercepts. Then we connect with that parabola shape. And then we could have a problem like this that deals with a max or min. Remember, if it opens down, if a is negative, the parabola at that vertex is a maximum. If it opens up, a is positive, then the vertex is a minimum. So in this case, we have a revenue function. R of x equals -2x squared plus 100x. Revenue is money coming in for a company. If we sell a product at X dollars, this product, we want to find the maximum of this product. We want to maximize the revenue. Since R of x equals -2x squared plus 100x is a quadratic function, and a is less than 0, a is equal to -2 and is less than 0, it means it opens down. So the vertex is a maximum. Since it's in standard form, we use the minus b over 2a formula. So -100 over 2 times -2 gives us 100 over 4, or 25. So at x equal $25, we've maximized the revenue coming in. So how much is that? Well, let's find out. So if we sell this product for $25, how much revenue do we have coming in? So let's see, y equals -2 times 25 squared plus 100 times 25. Plugging that into the calculator, we get $23,750. So this means if we sell the product at $25, we maximize our revenue at $23,750. Hopefully this helps you. Good luck with your exam, and we'll see you on Monday next week.